All right. Apologies for the delay, everyone. Hello and welcome to another episode of GPU Mode. Today, I'm really thrilled to have like some folks from the AMD like research team, like Rad, to talk to us about Iris, which is like a first-class multi-GPU programming experience in Triton. So there's already been people playing around with this library in the server when it comes to the AMD like multi-GPU kernel competition, specifically to sort of use like shared memory and stuff because it has like this like nice like Pythonic experience. So today on the call we actually have like three. We have the three of the creators of the library. So we have Mohammed Awad, who's having technical issues, but hopefully should be joining us soon. Brandon Potter, and then Mohammed Osama. If you have any questions in chat, like please drop them, and we'd all be happy to answer. So thank you, and Brandon, Mohammed, please take it from here.
Okay, awesome. So I'll be starting us off, but hopefully Mohammed Awad can get the technical issues sorted out and he'll take over. But today we'll be presenting Iris, first-class multi-GP programming experience within Triton. This is work done by Mohammed Awad, myself, and Brandon within AMD RAD. We're very excited to present this idea of how we're making multi-GP programming simpler using Triton's abstraction, using existing Triton's abstraction. So to start us off, I'll kind of give a takeaway slide. If you'd like to kind of get essentially a summary of what Iris is, it is really well encapsulated within this slide. So Iris is an open source Triton-based framework, and as Mark mentioned, there are already folks using it. It is a Triton-based framework for remote memory accesses. RDMA support is in the works. It is written in only 370 lines of code, and Iris provides SHMEM-like interfaces within Triton for multi-GPU programming. And one of the core principles we wanted to kind of embody within Iris is to make sure that we make multi-GPU programmability the first-class citizen within Triton. So maintain programmability and retain the performance that we get also. It has very familiar PyTorch and Triton-like APIs for both host and device-side abstraction. And it allows you to really get into the weeds and do fine-grained multi-GPU programming. And I'll talk about that in a bit. The contemporary approaches, which will most likely like go through as in the presentation compare against are based on stuff that Rickel does, or this bulk synchronous programming model, where you have on the left-hand side, I show a little code snippet of you set your device, you launch a compute kernel, you wait for that compute kernel to fully finish, then you launch your communication kernel, then you wait for that communication kernel to fully finish, and then you launch your other work that you wanted to do. So it's a very stop and go kind of model, the bulk synchronous model. That is mostly standard right now in a lot of different places because it allows sort of this portable abstraction where you can create collectives and you can use them as ops. But there's a lot of problems with it. It is CPU initiated control path. There's host and device side synchronization required, and it is like bulk synchronous. So there's a very stop and go kind of thing going on. And there's a lot of inefficiencies within it. This is what we are sort of moving away from, and Iris is one worldview of what that new model looks like. So within Iris, what the code would look like is on the left-hand side, a small snippet, where you're really within a kernel. You're doing some compute at a workgroup level or thread block level granularity. You're doing some compute. And if you need to do multi-GP communication, after you've done that compute, it really is a simple store or load. So you can do a compute, you can store it to remote GPUs, you can do more compute, you can load from remote GPUs, and so on. It follows a really natural workgroup-centric kind of programming model that Triton already embodies and extends it to support multi-GPU programming. It does not require any intermediate buffers that way. It doesn't require any sort of communication over the synchronization overhead. It really just is one fused kernel that you can write these kind of patterns with. So what Iris aims to provide is device-side primitives to be able to achieve a code something like this. And there's a more detailed example later on. The four principles that we looked at when we were building Iris were, first of all, we wanted to make sure that it is clean, it has minimal dependencies, and it is very, very simple APIs that anyone can understand. Anyone with a Triton background will be able to pick it up really easily. So that's designed by experts, built for scale. The clean abstraction essentially kind of talks about more on sort of the Pythonic APIs that we have extended for the host side stuff, and the Triton style device side APIs that allow you to do multi GPU load and stores and atomic ops. It is built on a symmetric heap implementation, all within Python. We do provide examples for collectives. So in the example folder within the Iris repo, you'll find lots of examples that do all scatter, all reduce, all to all communication, and things like that. But right now, that's not necessarily the goal of the framework. The framework's goal is to provide device-side APIs to do multi-GPU. You can build collectives on top of it, and we have also noticed that potentially in the future we might be able to provide those collectives as a standalone useful thing that you could just include and just use. These patterns, when we were implementing these examples, showed up time and time again. For example, like the actual collectives, like all to all, but also various ways to do locking mechanisms and lock variants to make sure that the communication has happened, and make sure you can load from a piece of data or store to a piece of data, and so on. The other types of patterns that we show in our examples, and what we have really evaluated our work on, is this fine-grained gem plus communication overlap via workgroup specialization or thread block specialization. And lastly, Iris's design is really built to scale. So currently we support a single node backend, so you could do RMA stuff. And we have plans for scale out to do multi-node stuff that is in progress. Okay, yeah, I'll skip through some. Yeah. Again, the programmability was one of the fundamental focuses of when we were building Iris. So it is really a clean, simple, familiar interface, and I'll show examples of what that looks like. So on the host side stuff, like I briefly mentioned, it has PyTorch-like tensor creation. So it extends what you can essentially do with torch.full to create tensors on GPU. From the host side, it uses the exact same interfaces as before. So in this case, you can just do iris.full, and you will have a tensor that is allocated across all of your nodes within all of your GPUs within a node. And it supports other Torch APIs as well, such as 1, 0, zeros like, A range, line space, and so on. So the very familiar PyTorch-like host interface works really well in our favor by just extending it and supporting multi-GPU variants of them. Similarly to the host side stuff, the device side also looks very similar. So we support Triton load and store APIs. So what load here is really implying is we had to make a few changes for it to work across multi-GPU. So for that, the only differences you see here is the two rank, from rank, and heap basis. So Triton had already had a declaration of what a load API looked like, and we have introduced the ability to use that load API across different GPU ranks. And for that, we had to add these sort of additional parameters to the actual API.
Oh, what's a heap base?
I will talk about that in a second. Yeah. So these three parameters is what you have to kind of carry around. In fact, the 2 rank and heap bases are just kind of a property of what limitations of current Triton. You can technically just hide these behind the point a class as well, but right now that's not necessarily supported. But even with just these minimal changes, the APIs still look very familiar. So if you have used Triton before, this should look very, very similar to you. So you're just doing a Triton load, but instead of doing a Triton load, now you're relying on iris.load to do remote communication. And yeah, I'll talk about heap bases. Yeah. So the core of Iris's implementation is built upon the idea of symmetric heap. So symmetric heap is a PGAS, so partition global address space abstraction, where the key idea is that when you essentially create a symmetric heap across all of your you create one symmetric heap across all of your GPUs, where you know a certain offset of the heap bases, and there's two sort of offsets that you have to keep track of. One is an offset of target's process heap base, which is for a given process ID, where does my virtual address space begin? And then the second set would be for a given variable, where that variable resides within that heap. So in this case, your process one, process zero, process two starts at this offset, the offset denoted by the heap base offset. And then if you're trying to look at for a variable called tensor x or whatever, that would be an additional offset on top of it, which will calculate where that variable exists within that large allocation. So all of Iris's implementation starts off with an instance of allocating this heap, and then all of your operations now work on that heap. So any kind of stuff that you do within Iris, that would work basically using this symmetric heap programming model. The offsets, or the bases for the heap address, must be first shared across all of the processes. So you have to start the program off by doing an all gather and getting the starting offsets for all of your various process IDs. And once you have them, that gets passed into these APIs, and these there's a translate calculation that's done to figure out where the memory resides in a remote rank. And I'll show an example of that. So on the implementation side of how we actually get.
Sorry, Mohammed. Sorry to interrupt you. Mohammed's actually here, so we
awesome.
finally have all three speakers.
Thank you.
Welcome. Nice to see you.
So Mohammed can take over actually from heap base's abstraction. That'd be perfect.
Okay, I think I need to share my slides.
Yeah, just slide, and then I can pull up your screen.
Okay.
Is maybe now a good time for me to ask questions? I had a bunch already.
Yeah, go ahead.
Okay. So my first question is that, like, 360 lines is super impressive. And so, like, what I was like thinking, like there are some other libraries that I've seen, like Yifu Wang, for instance, now thinking, had like a couple other slides, had like a sort of small symmetric library in PyTorch. There's like libraries like Triton distributed. I'm sort of like wondering if you could comment like briefly on the trade-offs like of these various libraries.
I can fill this one. So the implementation with these APIs is directly done in Triton. So you can do things if you're tightly integrated in with Triton that you can't necessarily do if you're calling into other APIs like Triton distributed. So for instance, like these load store APIs, they're being jittered by Triton, and they're going to be generating like a kernel with these address calculations that are like directly embedded into them. So when you're dumping out like a Triton cache, you can see all of the inline assembly that's been generated. You can see it is generating as like a single kernel. So there will be slides later on that will show some like special things you can do with cacheability with some of these like load store APIs, which are very useful for getting like the last little bit of performance out of the library that you can't necessarily do if you were doing something where you were delegating it to a third-party library.
I see. And it's a sort of slightly related question. It's like, I think Mohammed had shared a slide showing a user-facing API where the initialization of memory looks very similar to what it does in PyTorch. Like, are those actually PyTorch operators for context? Like, basically, is it like a sort of a detensor-based thing, or are those just like PyTorch-inspired like APIs for initializing memory?
We'll show more examples in a few slides, and I think that question will be answered. But they're basically PyTorch-like APIs.
Okay. Last question, then I'll let you go, Mohammed, I promise, which is that like so the other Mohammed mentioned that like you have examples of collectives in your repo. And so a very noob question here. I'm not a distributed systems guy, but like my understanding is like basically collectives, nickel, Rickel like is like a different programming model from like shared memory stuff. So would you actually want to implement collectives using shared memory, or it's more of like you can kind of thing?
I think we're exploring that. I think we're like we have implemented a bunch of examples already, and we already see the patterns. So it seems like there are patterns for collectives, there are patterns for acquiring and releasing log, for producer-consumer relationship. So we might eventually introduce those. I don't think we have decided yet, but I know maybe others have thoughts as well on that, Muhammad or Brandon.
Yeah, I think I can add a little bit. I think the key thing is that collectives could, like the Rickel, or at least the traditional sort of bulk synchronous way of doing it is very much like providing an op that you just call. What we are trying to do is maybe find patterns that exist at a workgroup level granularity that will have really nice implementations, performant implementations that would be used across various different applications and workloads that you could just call into. If you're writing code in Triton, you could essentially just leverage an existing implementation rather than constantly rewriting the same set of code using Iris's device-side APIs. So that's kind of what the goal there is.
I think the key thing is that we're only going to be providing device-side APIs. I don't think we're going to be providing like host-side APIs, because it doesn't make sense. At that point, you're just basically competing with Rickel, which is not like what we're trying to do.
All right, that sounds great. Okay, I will let you guys keep going to the slides. Thank you.
Okay, thanks. Apologies for the Wi-Fi connection issues, but we'll go next slide.
Yep.
Okay. Yeah. So the implementation of the library is actually very simple. I think once you understand it, once you understand the next few slides, you should be able to understand every piece of line in the code itself. So let's start first with some with the load API. So the load API looks like this. It's basically you have the signature, as Muhammad probably explained, and then you have the first thing you do is that you just do the pointer address translation. So that's the first line of code here, and then you simply do the load or store here. So the load store here is going to be across XGMI, for example, if you're translating across strings. But the most and like the other APIs as well, like load store, bot get, atomics, all of them, they will look very, very similar. All of the functions basically are a series of translation than the operation itself. Now, the most important function in the entire library is translate. This is the critical function. It's literally the function that any operation will go through. So if you understand this, and if you're interested in the backend library itself, then this is really what you need to understand. So it starts with just loading the heap bases. So you load your current rank heap base and the other rank as well. And then you compute the offset. So you take the out pointer that you are trying to load or store from, you subtract it from your heap base, and you get the offset, which in this particular example, it's hex 448. And once you get that number, all you need to do is just you need to add it to the destination heap base. So you just add it to the heap base of that destination of the two base. You add the offset, which is 448, and then you get the translated pointer. So there is some casting here, but that's basically the whole idea is to just do some very simple pointer arithmetics to compute the translated address. So that's, if you understand this, you really understand like the entire device side backend for the library. This is really the most important thing to understand. And I think one of the questions that people usually ask is like, okay, how you implemented that in Triton, how close are you to what you can actually achieve in heap, for example, or close to the hardware peak? So we run those benchmarks to make sure that we kind of evaluate that. So the benchmark is showing point-to-point operations, load and store. Let's start with the left one. So the left one is showing, for example, if we look at the bottom left square, it's showing the bandwidth between node 0 or GPU 0 and GPU 7. So to get from GPU 0 to GPU 7, you have to go across XGMI. So here, for example, you're achieving 96.3% of XGMI bandwidth. If you look at the top left corner, you see the same 93.3, but this number is between GPU 0 and itself. So it's basically you're reading from HBM. So the diagonal in this figure is basically memory access through HBM or your local memory. Off diagonal is across XGMI. So that's the explanation of what we're looking at here. And the goal is to see numbers closer to 100%, right? So if you see the numbers on the diagonal, they're very close to 100%. So they're close to the HBM peak bandwidth that we can achieve. Off diagonal, they're also close to 100%, which is exactly what we need. So we need to see numbers that are close to 100% so that we can validate that the implementation does not add any overhead. And Triton, that just the fact that we're implementing Triton is not adding any additional overhead. So hopefully you can see that here. Same thing for Sora as well, same benchmark. Diagonal is showing bandwidth that you can get, its local bandwidth, so it's HBM. Off diagonal is XGMI. So again, the numbers are close to 100%, and that's here what we want to see. So we like to show this pretty picture to people so that they can actually say, okay, it's not adding any overhead. But at the end of the day, what we actually look at when we're writing this benchmark, we look at the assembly, and the assembly is the ground truth, like the source of truth for us. So we know exactly the load, as the operation, like the code, the assembly that gets generated for load and store, and we know that that's exactly what we want. So this should give you a little bit of extra confidence that, okay, we actually know what the code generated all the way down to the assembly level. We have a lot of other, so the load store, obviously you're just doing the load store, but then you need to synchronize. So then comes atomics. So we have a bunch of atomics as well. So we implemented a bunch, and I would actually, since we made the project open source, we had an external collaborator who has been kind enough to actually implement a bunch of those for us. So most of those actually are implemented by someone from the open source community who are just kind enough to just implement them for us, and we're so grateful for their work, of course. But these operations, they're atomics operations, so hopefully you're familiar with the ones in Triton, and they're straightforward. We're going to discuss the key things that you look for in a few seconds, but those hopefully look familiar and they look similar to the ones for the loads and stores, which we have shown earlier. Okay, so I was supposed to wait here for a few seconds to make sure if there are questions, we can answer them. So let's do that anyway. Let's see if there are questions before we move on to the next set of slides, which is going to be like a hello world example.
Sure. Yeah, I had a question, which was, could you just comment on why are atomic operations important again? I think I missed that connection.
Yeah, so it's going to be clear in the next example, but it's basically the way for you to, basically at the end of the day, the pattern is going to be you produce some data, you set a flag, the consumer is going to wait on the flag and consume the data. So that setting the flag and observing the flag is atomics operation, and that is why it's important. It's going to be clear in this.
All right, so I see two questions in the chat. I'm going to pull them on the screen. Let me know if you guys can see them.
Is processing, yeah. So I think rank, process, GPU, they're all kind of interchangeably. In that context, we're kind of using them the same. You can implement it in different ways, but in this particular library, they're kind of all the same.
All right. And then I see this other question from Vipul Sharma. Oh, sorry, no, I'm just gonna go in order. Vipul Sharma.
The load score for source union was somehow lower than XGMI. Yeah, I mean, these numbers are normalized. So like when you see here 93%, that's relative to XGMI bandwidth. So these are not raw numbers, these are just percentages.
And then one more question.
Okay, that's a good question. That's a very good question. Let me see how to answer that.
I can answer it.
Go ahead.
So it's going to vary between architectures, and it depends on things like loop unrolling as well. So Iris or Triton, because it's utilizing Triton does a very good job of doing like a certain number of loop unrolls for the waves that are executing these ops. And the amount of SMs that you're specifying will be based on the number of like tiles that is transferring as part of the algorithms that it's operating on. So it will take, depending on how much unrolling you have, it typically takes like tens of CUs or tens of SMs to hit like full bandwidth for XGMI if you're doing like a loop unrolling for stores. Say like you did like a loop unrolling factor of 8 and you had like 10 CUs, 20 CUs, you can usually get close to the XGMI bandwidth. For the HPM bandwidth, it's typically more because you're having to generate more loads and stores in flight to fully saturate the HPM. But it'll vary between architectures depending on the architecture specifications.
Yeah, and I'll just add that so that I think the goal from this presentation is to make sure that people understand everything. Like adding more CUs to do load and store is not always going to help you. So you're going to have to figure out the right balance between like overwhelming the network or just issuing like just the right enough number of loads and stores. And like Brandon said, it really depends on a lot of things.
I think one other core point to add is that in Iris you have the ability to actually control that. So that's super important. To be able to express that is one key principle, and that will show up in some of the later parts of the presentation as well.
All right, I think we can keep going then.
Okay, so we're gonna discuss the hello world example, and really, this is really the most important thing that I would love for you to understand very, very well if you're not already. So at the heart of any code that you will write, this is the pattern that you will see over and over again. So if you understand that well, you will solve any other problem. This is the most important thing. So let's look at the code. So we start with the initialization here. So like Mohammed mentioned earlier, we're gonna have to do some initialization in the beginning, and in our case, we're just using the torch distributed like library to do the initialization for us. So that's the first line. We need you to initialize that for us so that we can do the very initial setup of communicating the heap bases, and then you construct Iris. So Iris instance, once you do that, it constructs the symmetric heap. It does the initialization and all of that, and it allocates basically like the backing store, which is simply like a PyTorch tensor that we will slice from in the future. And the next line of code, when you say input equal Iris to trend end, so basically you took a slice from that backing store that we have. So what you get back here is basically like a PyTorch tensor. It's a PyTorch tensor. It's like a native PyTorch tensor that can do whatever you want with it. So it's the only special thing about it is it's allocated in like fine grain memory, which is memory that we use for fine grain like synchronization. And it is also allocated on the symmetric heap so that we can figure out how to do the translation. Similarly, flags as well here is done through the Iris API, so Iris of zeros. So again, you're getting like a PyTorch tensor. So the most important thing here that I want to mention before moving forward is that once you allocate a tensor on the symmetric heap, if you have to use that tensor. So you have to be careful about doing operations on that tensor that would return a new tensor. So you have to always use in place operations on the tensor, because basically if Torch decides to reallocate the tensor, it's gonna be outside of the symmetric heap, and then you cannot do any RMA operations on it because we cannot do an address translation. So just something to keep in mind if you're using Iris APIs to allocate tensors, and you have to for RMA operations, you have to be careful about APIs that basically Torch API is a reallocate tensor, so you will always have to do things in place. So next, we're gonna launch two kernels, and here, like the rank number 0 is gonna launch the producer kernel on one particular stream, and the consumer or the rank number 1 is gonna launch the consumer kernel on the consumer stream. So technically, you don't really need stream here because these are just running on two different GPUs, but I think it's good practice to use the streams. And that's basically it. That's the host side setup. That's all to it. On the producer side, you have some computation maybe, so you prepare some data and you're ready to share it with other ranks. So what you do is you just use the the Iris store API. So here you're saying Iris store at the pointer, store some data, and here is my rank, which is 0 in that case, and I want to store at rank number 1. And here are the heap bases. That's basically all you need to do to reach out to memory that is across XGMI or somewhere else. So these stores are basically relaxed stores, so they can get reordered by the compiler. And for you to actually be able to do the producer-consumer relationship, you have to use atomic, or the right way to do it is to use atomics with acquire and release semantics. So if you're not familiar with like acquire and release, basically release here, which is like the last line, iris of atomic cache, it basically means that please do not reorder any memory operations before this line. So basically you're saying, okay, please make sure that the stores reach the coherence point before you set the flag to notify others that they are ready to consume the data. So that's what release means. Scope equal system means that we're gonna do the acquire and release between two different GPUs. It's not on the same GPU. So the scope could be like system, could be GPU, could be wave front, could be work group. But typically, if you're gonna do like communication with Iris, you're gonna be doing stuff usually across system scope. Now on the consumer side, the consumer, which is running in a different process, is just spinning, waiting on the flag to be set to 1. And once it sees it's set to 1, it's gonna actually consume the data. But what I want you to see here is that the semantics here is acquire and the scope here is system. So there is this pair of release and acquire. So again, the acquire here means please do not reorder loads above me. So basically saying, please make sure that I first acquire the lock and then I consume the data. So basically, once you exit out that loop, the data is ready for you. And this is really like the core example that I really want you to understand very, very well. So just to reiterate again, the atomic cache with acquire scope, it essentially synchronizes with the atomic cache with release scope, which guarantees that the data that you have written on the left is the one that you will consume on the right. So hopefully I explained that well, but I really want to make sure that this was understood very well if you're not already familiar with like scopes and semantics. So I'm gonna wait a few seconds before we move on to more complicated stuff. But again, this is really the most important thing that I hope you understand. Okay, so let's just move to the next slides. So once you understand that better, you can implement a lot of things, and actually we have implemented a bunch of them.
Mohammed, there's a question. Maybe we can answer that before we move on.
All right, let me pull it up.
Why are explicit semaphores exactly compared to PyTorch? So, I mean, I assume when you're talking about PyTorch, you're talking about like host side stuff, right? So it's driven by the host. I mean, so technically you need to synchronize on the host, but you synchronize with a different way. You synchronize maybe with the like a torch device synchronize, for example, or things like that. You need that synchronization because you have threads all running in parallel, running concurrently across many CUs and multiple GPUs. So you have to have that. You have to have the semaphores or the locks to consume, to be able to know exactly when the data is ready to be consumed. So this is just parallel, like just because you're doing parallel and concurrent programming on the device.
Yeah. So one key difference could be that maybe I think that what the question is hinting towards is that on the host side you would probably need some sort of kernel barrier, but in this case, since you're in the device world, the Triton.jit tag above the function producer kernel and above the function consumer kernel, there really is implying that this is like a GPU kernel, and in that GPU kernel we're doing a fine-grained synchronization between a producer that's on one GPU and a consumer that's completely on a separate GPU. So you need explicit semaphores to make sure that the consumer sees the data when it's ready and actually is able to consume it.
These atomics, these synchronizing atomics, are like the standard way to synchronize between GPU threads using AMD's memory model. If you look at the LLVM AMD GPU backend compiler documentation, these atomics are the memory model like building blocks that are used to synchronize threads in our GPUs. And this Triton wrapper is just a wrapper around those atomics. The order and the scope are specified there in the parameter list, but they're really just the level synchronizing.
I guess like related to this, like for me, like I just have a question on the interrupt, like because like you have like this like like Triton decorator, but then like inside the function you're calling like you're calling iris functions. So like was there like a lot of work y'all needed to do to like support this with Triton, or basically assuming just everything below it is written in Triton and in Python, like life is good and that's it.
The atomic gas and all of these functions, it's basically the code that we showed earlier. It's really just like that simple. So I don't think it was any trouble. More recently we're actually have been running into maybe a little bit of trouble because we want to support like the cache modifiers and other things as well with load and stores, and this is a little bit it's I mean we have found a solution, but that we had to maybe have some workarounds around around some issues. So generally speaking, yeah, it was straightforward until you do something with strings, for example, or something like that.
I see. All right. Then I think we're good. Like we
Okay.
should perhaps move on and come back to more questions.
Okay. So let's dive into the patterns. And yeah, so if you're competing, this is really the most important thing that you should understand. So hopefully by the time we got here, you understand that you're not gonna get the best performance unless you do computation communication overlap. I think this is just a must that you have to do. Now, how do you do it? There are just many ways, and we implemented Iris just to make sure that we can very, very quickly and very rapidly iterate and try different things. And I'll mention how fast we can do it at the very end. So we wrote down this taxonomy for the things that you or the patterns that you can do, and here we're just considering like a gem plus all scatter. So here on the right you see the operation. Basically you have the A matrix replicated across ranks, and you have the B matrix sliced in the column, like column wise. So you multiply A times the slice of C, then you get sorry, times the slice of B, you get the slice of C, and all you need to do is just scatter the C, the result, the tiles to all of the other ranks. So looking at the patterns, how can you do that? How can you? What are the ways you can achieve that? You can do it either in a few unfused fashion, or you can fuse. And if you do it in unfused fashion, you can do it in a bulk synchronous way, or you can do it on what we call a producer consumer way. So we're going to explain all of that, and we're going to show examples next. If you decide to fuse, you can fuse sequentially. So you have like a GPU wavefront or work group doing some work, then sequentially doing the communication. That's one way of doing it. If you do it in a producer consumer style, you can do work group specialization, you can do wavefront specialization, and you can do interesting things. And like if you're too clever, you can do something like a work queue. We're not going to talk too much about that. So yeah, so today actually you cannot do with specialization just inside the Triton. However, you should be able to do it inside Gluon, but we don't have like a Gluon implementation yet. So let's dive into these patterns. And again, this is really the most important part of the talk that explains to you how you get better performance and how you do the overlap. So first of all, let's just start with the simplest one, which is just unfused bulk synchronous. So we're basically doing what you could do with Rickle. And here's how it looks like. So you launch, so you have basically from this particular GPU perspective, you just launch a bunch of computation. So here we have 5 CUs. We launch a bunch of gem tiles that gets executed. And once you finish that, there is a barrier. You wait for the computation to finish, and then you launch your communication kernel, which is here, the all scatter. So how does that look like in code? That's it. This is the code that you have to write to get there. So you have obviously this. We have removed some of the things here, like the hence and so on. But like at the end of the day, this is like the actual code that you need. So you have on the left there is a gem. There is a gem loop over the number of gem SMs. Here, just gem SMs is for generality because we're gonna reuse this code in the future. But here, gem SMs is basically the total number of SMs in that GPU. So maybe on MI300X, that's 304. So you compute the gem, you do the accumulation over C, and then you have the C result ready. You just store it in global memory, and you're done. So on the left is basically just your normal persistent gem kernel. On the right-hand side, this is the communication kernel. So what it does is that it iterates over the tiles as well, and it's a persistent kernel, so it just occupies a number of SMs in the on the GPU and just iteratively keep like finishing up the work. Here again, the COM SMs is basically 304 because we're just using the entire GPU, but we will see in the future what happens if we change that number. But basically here here you don't need the semaphores because you had that hard barrier on the CPU between the two kernels, because if you look at the launch kernel at the bottom right, you launch persistent gem on mainstream and then you launch persistent all-scatter on mainstream. So they already have like some they're already established like an ordering from the CPU side. So all scatter kernel is simply just gonna load the tiles, and what it will do is that it will iterate over the ranks and it will just scatter the data. And since we already have the data in our local rank, we don't need to store it again. So this is why there is an if statement if remote rank not equal to current rank. And other than that, you just scatter the data across.
Can I just jump in real quick and say something related to like stream synchronization and versus doing things like at a fine grain level? Because there was another question in chat. When you're doing things in CUDA streams or HIP streams, when you launch a kernel and it produces data, as part of the end of that kernel, it flushes data out of the caches and makes data visible. So if you had data that was like stuck in an L1 or an L2 cache within the GPU, and then you ended that kernel, like the assembly for that would be like an in program instruction. As part of that instruction, it will flush out the cache hierarchy out to like the memory visibility point, and then subsequent kernels should be able to see any data that was produced. That's stream synchronization. Is like this coarse-grained model. When we're doing things with these low-level atomics, these synchronizing atomics, there's no the kernels don't necessarily end. They can be co-resident on the hardware. So to ensure that data is visible from the GPU, you need to flush it out of the caches or the different like memory levels to make sure the data is visible. And so when you do things like a release or the acquire atomics that you were showing earlier, that's actually making sure the data is pushed out to visibility point for the other kernel to see. So that's related to some of the discussion that we were having before.
Yep. Thank you. Okay. So, well, this is just the bulk synchronous one. How fast can you get? Well, you actually get some slightly performance gains. So ideally, we think that, ideally, we would have thought that you should at least or at max match Rickle's performance. But sometimes we actually beat the Rickle or the bulk synchronous implementation of just torch.matmul and just Rickle, for example, on the bottom left, we're here beating it. But obviously, like Rickle and torch.matmul, these are generic implementation. They have to deal with a lot of shapes. So they are not specialized at that, like our kernels. For our kernels, we can specialize it and we can make tricks that a library that is designed to run any problem size cannot make. But this is really the important thing about Iris. Iris lets you do all of that. It lets you write the kernel in the very custom way that you want. So even if you want to customize your kernel for some particular shapes or some particular things, you can use Iris to even get that performance gain. But again, there's obviously that trade-off of general purpose library that is designed to solve very, very many problems versus like your own particular solution that is targeting the particular problem. So obviously everything has its trade-off, but if you already know some things about your problem, maybe you can take advantage of custom solution to get better performance. But more interestingly, we look at the other patterns, which is the next one is producer consumer. So we actually are gonna use the same code, or actually let's first look at the how it looks like. So you essentially partition the GPU between compute and gem. So if you look at the figure here, we gave the gem 3 CUs to do the gem computation, and we gave the communication kernel 2 CUs. So once you launch the kernel, was obviously here you're launching two kernels on two different streams to establish concurrency. The kernel that is doing the gem, that is producing the data, it produces tile 0, tile 1, tile 2. The communication kernel, if you see here, they're just sitting, spinning, waiting for the tile to be produced. And once they are produced, they consume it. So you see here the arrow with the yellow. Once tile 0 is ready, the lock is ready to be acquired, and the communication kernel consumes tile 0. And maybe here it will do an all scatter or use or whatever it needs to do. Same thing for tile 1. The next time step, tile 2 is already produced. So you see like this very, very small log box because the tile is already produced in the previous time step. We can already consume it. And then tile 3, you're going to have to wait a little bit until it gets produced. So the key things here that you want to think about is how do you partition the GPU between compute and communication. And I mean, this is an interesting question, and there isn't really like one answer. We have some ideas on how to do it, and there is usually some good intuition for how to do it. But yeah, there is some art to how you do it, and maybe there is some mathematical way to actually figure out the right balance between the two. So that was the producer consumer kernel. Here is how the code looks like. So if you see, this is basically the same code that we have seen earlier. The only difference here is that we just set the number of GMSMs to not 3 or 4. For example, you could set it here, for example, to 56, for example, a nice number that divides nicely with interesting gem shapes, and then you can leave the rest for COM. So again, you on the producer side, you're just computing the gem. You're using a fewer number of compute units than what the GPU has. And then once you finish the computation, which here you're writing with this write-through modifier just to as an optimization to not pollute the cache, and then you do the release pattern where you just release and you said that okay, this tile or the log for this tile is now free. The consumer who is waiting on the right-hand side, once it sees it, it will acquire the log and it will consume the data and it will do the scatter. On the host side, you're just launching 2 kernels on 2 different streams to establish concurrency, like I mentioned earlier. So how good does that give you? Well, you get some very good performance gains. So for example, if you look at the top right, you're getting here like 2.5x speed up. And again, there is obviously, how do you partition the problem? We haven't even tried to address that here. We basically, I think Muhammad is the one who actually wrote that code, and he just had some good intuition for how to split the work. So I think he did 256 and 304 minus 256 for the communication. But there is, I mean, you can even push this further if you want, if you know exactly the sham shapes that you're dealing with, or if you have a good way of determining how to partition. So we can talk more about partitioning at the very end, but I'll go on for now. I think next is if you fuse. So far we haven't been fusing kernels. So we had like 2 kernels to do one kernel to do communication and 1 kernel to do communication. This time we're gonna fuse kernels, and the first way to do it is just sequentially fuse the 2 operations. And this is actually the easiest code that you could write. So in this particular example, you're launching a single kernel, and what that kernel does is that it does the gem operation, and then once it finishes that gem operation and it has the tile in its accumulator registers, it can just do the all scatter to all rank. So that's the communication kernel afterwards. So obviously it's very easy to write. You avoid the fact that you have to go through HBM because the data is already in registers and you can just consume it right away. However, you are also that model of just writing uber kernels that also has its own problems, right? So you're very likely increase the register pressure. And if you have some tail effect, like one here you see here, that tail effect will also get worse because now your kernel is running longer. So again, there is an art for how to actually do tiling and do splitting of work, which is like a big topic that I'm sure actually I'll ask Muhammad to actually comment on it once we finish the slides.
Before that, Mohammed, do you mind using a pen or laser pointer just when you talk?
Where is it?
I think you can use the PowerPoint one. If you right click on the PowerPoint, it should show.
Oh, I'm using.
That should work. Yeah, like the settings.
Unless you're sharing directly the slides.
No, I'm sharing the PDF.
Oh, okay, never mind. Sorry.
Okay, well, sorry. I'll try to be more clear about where things are. Okay.
I say that because if you go back to the slide, I think the tail effect is very important to understand.
Yeah.
It's that empty black region underneath the CU0, compute unit 0, the second sort of time step. So the last gem plus com is only issued on CU0, and everything underneath it is an empty, like unused resource region, and the synchronization of the kernel boundaries at the very end of that. So all of that computation all of those resources are essentially going to waste unless you have other concurrent kernels also running at the same time on top of this gem and com thing. And that could be a very big problem for fusing it in the sequential way, where you can't slot things in between various orders to kind of Tetris it nicely.
Yeah, thank you. Okay, so here's how the code looks like. You, on the left hand side, you're just producing the gem tiles like we have seen before, but this time you don't have to write to main memory because you fused it already. You have this uber kernel that you can ready to send the data across. So on the right hand side, what you need to do is just take the C accumulator register and just scatter it across all ranks. So for your own rank, you can just use TL.store because this is just a local access. For remote accesses, you can just use iris.store. And I mean, you can use also iris.store for your local address, but you can do it this way as well. In terms of launching the kernel, there is just one kernel, so you just launch the kernel in one stream, and that's basically it. So this is actually like the simplest code that you can write. Like fusing is actually so simple, particularly with Iris. If you're using the Iris API, it just lets you the communication part is simply these few lines on the right hand side. That's basically it. That's all you need to do. All you need to append to your gem kernel. So how does that look like in terms of performance? So it varies. For example, on the left-hand side or the bottom left-hand side, now we're getting good results with that particular implementation. If you look at other points in the graph, it's not always the case, right? I mean, it seems like we're always getting good speedups compared to the reference implementation, but not always. And again, there's probably many reasons that could affect that, and one of them is maybe like the latency effect when your problem size is not divided nicely, or maybe you add some register pressure. So again, there are a lot of trade-offs for one solution versus the other. Okay. Now, the last way you could implement this is, again, you fuse, but you have a producer-consumer relationship, and you do wave workgroup specialization. So I think Muhammad, when he presents this, he said this is his favorite, and it's also my favorite. I think it's very neat. So here's what you do. You launch a single kernel, but that single kernel, at the very beginning of it, it has an if statement. It says if my block ID is less than the number of CUs I assign to computation, I'll do computation. Otherwise, I'll do communication. So here, CU0, CU1, CU2 took that if branch where, okay, we're less than 3, we're going to do computation. The consumer side is just waiting until the tile is produced. So it kind of looks similar to the producer consumer in terms of like the kernel concurrency, but here it's happening inside one kernel.
So question there to both of you guys then, which is that, like, I think we had a question from Arseny asking, like, hey, can you figure out the right compute, like basically the right allocation between consumers and producers automatically with the compiler? It sounds like you don't need to, because you just basically have like a queue effectively, and you just fill it up. Is that right?
So there's I think Muhammad will want to answer that question. So
yeah, I can answer that question. I think the question in the chat talks about potentially micro benchmarking, essentially, to figure out the compute and comms, which happens a lot for gem kernels, for example, when you're trying to figure out the tile sizes. At least I personally fundamentally believe that it's not the right approach, because it requires obviously running the thing once, figuring it out, caching the result, and then using that later on. It works in some cases, but maybe not ideal for most cases. What we'd really like to figure out is essentially this compiler-based approach, where we could do some analysis ahead of time and use an analytical model to predict what that partition looks like. Or you could do something like a work queue, like you mentioned,
Yeah.
where you, as work gets created, you fill the queue, and work groups are essentially just picking up whatever the next piece of work they have to do, therefore perfectly utilizing all of the GPU entirely, and not have to figure out this division manually. So yeah, there's a number of approaches there, and we're exploring all of them. And yeah, it's a very interesting space.
Oh, very cool. Okay.
Yeah, but we do really like, just like Muhammad, I also agree with him. I do really like analytical model ways, and I don't like doing that grid search kind of solution, unless your problem is very very constrained. Like if you just have like just a few shapes that you're interested in, maybe that would make sense then. But in general, I think like generic solutions is probably like an analytical model or a cube base that would be very clever, and the right thing to do, I think. Okay. So how does work group specialization look like? You have the code on the left. Let's start on the left. You basically have that big branch at the top. It says, okay, if I'm less than the gem SMs, I'm gonna do the gem work. Otherwise, on the right hand side, I'm just gonna compute my BI like program ID. So basically, just do the math to compute like your ID after subtracting the CUs that you assign to gem, and then you consume the data. So again, you still have if you still have the producer consumer relationship, this is happening between two work groups within the same kernel, not two different kernels. So this is just one kernel, and then you have the same relationship. So obviously, like if we look at the top right hand side, you're storing the C results once you finish, or the partial results, and then you release the log. And if you scroll down a little, and then like at the consumer side, you're iterating over the tiles and acquiring the log, and then with an acquire semantics at GPU scope, because we're communicating within the GPU here, and then you just do the all scatter. So again, when you're actually launching this, you're launching one kernel. So the host side code, you're just launching one kernel, but that particular kernel is parameterized over the number of CUs you assign to gem, or number of SMs you assign to gem, the number of SMs you assign to COM. And before we move on, I actually mention maybe something here. So I think there are actually like many ways to do optimizations on this. And actually, one of the things that I would be interested to see, if you could co-locate the the communication work on the same CU that produced the compute work as well. So maybe it doesn't, I guess you, in that particular case, you will have to do it in a non-persistent fashion, but maybe there is some trick to get some locality. I think that would be interesting. But even if you just do that, you will get some very good performance gains as well. So that's the last part on the last bar on the very right hand side, the purple one. So you see here some different results, mixed results between different shapes, but generally speaking, it's better than the bulk synchronous solution, obviously, because you're doing the overlap. But sometimes it's very large. Sometimes it's very nice speed up. For example, the bottom two shapes, you're seeing some very good speed ups, up to like 60% faster. Same thing as well for the middle right as well, middle top as well. You're seeing up to 60% faster. But there is no one single answer, right? So we shown these results, and which one should you use? Well, we have been doing analysis to try to figure out, okay, which one does it make sense to use and when. We don't have an answer to that yet. I think even if you just look at the 6 shapes that we're looking at here, it's hard to tell which one is best. So this is like a different problem. What Iris is trying to do, Iris is trying to make sure that you can explore all these solutions very, very quickly. So actually, Muhammad Osama, he is the one who wrote all of these implementation, and I think it took him like an hour or something to finish all of that. And some of these implementation, it took him 10 minutes. And he actually recorded that as well. So I'll ask him to share the video as well. I think the video was very good because he did a good job like explaining what he's doing. And I'll mention something about videos at the very, very end. But again, so that the goal from Iris perspective is to enable you to do all of that exploration very, very quickly. We showed you the code in the previous slide, and it's not a lot of code. The code exists on the repository. You can go check it out. It's not a lot of code, and you can very, very quickly iterate over different solutions and different clever ways of assigning works to blocks, or trying to achieve some performance gain through maybe like some clever thing about locality. But that's what Iris is trying to do. Iris is trying to give you the low-level APIs to empower you to do all of that. Yeah, so I think before we move next, because we're gonna discuss basically next steps and things like that, we can stop for a few seconds and see if there are more questions, because we're gonna stop for results. This is like our last slide on results.
I think I asked mine. I think there was one question I don't know how to answer, which was here. I'll pull it up.
Yeah, I can answer this. Yeah, so the split K and stream K, we have variants of all of these various gem schedules, and yeah, the approaches shown here work with all of those various variants. What split K is essentially saying is it's going to take like one of those the tail effect or tail occupancy effect that Mohammed was showing. That's when this question was asked. It would take one of those gem tiles and make smaller pieces of it to get better utilization across the entire GPU. Stream K fundamentally does the same thing. And yeah, you could utilize all of these different variants along with the locks that we describe and the pattern we describe, and it scales, or the code would work as is essentially. It's just going to the gem schedule will just look slightly different.
All right, I don't see any more questions. I think we can keep going.
Okay. So we've been having fun writing applications, and I hope you guys as well have fun writing applications and open pull requests. We have written a bunch of them. So you see here, we have written like the micro benchmarks. We had actually an intern, Okta, he implemented the flash decode. Actually, within his summer, he implemented flash decode, and he implemented all gather plus gem. And obviously he's a very, very clever, very smart guy, but it was effortless for him to implement those. We implemented all scatter as one as well. We implemented one-shot all reduce, atomic all reduce. We have an initial implementation for ring-based all reduce, still work in progress. The all gather plus gem, like I mentioned, it's pretty much done. Gem plus reduce scatter, we haven't implemented that yet. I would be interested in seeing that as well. We're very, very interested in implementing an MOE kernel. We haven't gotten that part yet. And we're very, very interested as well in seeing results in end-to-end workflows in inference frameworks like VLM or other frameworks as well. So if you're interested in any of these problems or other problems as well, we would love to work with you, either maybe try to figure out how to implement it or review pull requests you create or anything, where we're happy to collaborate with the community in any ways. And I know maybe some of these kernels are of particular interest to you guys. So we're not just interested in scale up. We have been thinking about scale out from the beginning, and I am a big fan of memory scopes, and I think they're the way that I want to write GPU code is just using scopes and using memory orders. And I have strong opinions about this, and I think basically what I wanna see for scale out and what we are trying to prototype is basically adding a scope for world. Obviously, this is like a heavyweight scope because it crosses the boundary of GPUs, but it makes programming very, very easy. And I think if I'm a developer, what I need to understand is I need to understand locality, and I need to understand the cost of synchronization. And I already understand locality. I understand that registers are faster than HBM, or faster than HBM, and HBM is faster than accessing something across XGMI, for example. Same thing for scopes as well. I know that scope or a synchronization at block scope is going to be cheaper than GPU one. It's going to be cheaper than system, and it's certainly going to be cheaper than world. So as long as I know exactly the cost of these operations, I think the programmability will be the thing that I'm looking for, as long as I understand the cost of those. So we're going to implement this world scope. I think it's very, very doable, and we have some initial idea on how to implement that. Iris will always provide low-level APIs for RMA and RDMA, so load and store, put and get. But we're gonna implement some collectives as well, just to continue the series of examples that we're building to make sure that people know how to implement those, and we can also explore if there are ways to actually abstract those away. And again, Iris will always help you to prototype like very fine-grained computation and communication overlap very, very quickly, even for RDMA as well. And this is our last slide. We're just gonna mention like the next things that we're working on. So we're still working on the library development. Like I said, we're super interested in integrating with inference frameworks. So this is like a decent amount of work. If you are maintaining a particular framework and you're interested in working with us into integrating that, we would be more than happy to work with you. So we're happy to work with anyone. And the second thing is obviously we're trying to work on a library improvement or productization. I think actually looking at the repository today, I'm very happy with it. I consider it like a decent product. So we have a good documentation. We have unit tests. We have CI. We have been improving things quite a lot. So there is always room for improvement, but I think I'm very happy with what we are right now. We're gonna implement scale out, as I mentioned. So those are the main core library development things that we need to do in the near future. In terms of application workloads, we're implementing things as we go. Every time we speak to someone and say we're interested in that particular kernel, we try to spend some time to implement it or provide guidance on how they implement it. And we want to see more example. We want to see more example across all domains from everyone. So we got an email a few days ago saying, "Can I implement this particular? I think it was bioinformatics kernel and add it to Iris as an example?" And the answer is always going to be yes. Please do write examples. If you write code that uses two or more GPUs using Iris APIs, I'll be more than happy to accept your code. As long as, of course, like there is documentation and you can explain the code so that others can understand it. So we're more than happy to accept BRs for anything really. And what I really want to finish with is that we did this project because we were just interested in making multi-GPU programming easy, and I think so far we have been successful. But the user that I really care the most about is the people who attend these kind of talks, the ninja GPU hackers who are just writing code for fun and just doing the very novel ideas and the state-of-the-art kind of research. This is built for you. We want to enable you to do all of that interesting stuff. So we want you to use it. We want you to report bugs. We want you to improve it. We want you to suggest anything, and we'll be happy to work with you. We really want you to help us drive the future of all of that. And Iris is always going to be open source. We're going to make sure that everything remain open source. All discussions, all ideas, all of them will be through either PRs, through like issues, or through GitHub discussions, and even we can discuss a few things on Discord as well, given that there is a competition and maybe people would be interested in brainstorming as an idea. So the key thing here is that I really would love to see people contribute and just open issues, and we really want you to help us drive this forward. And yeah, before I end, I think I also want to mention that, so Muhammad, I think I'll ask him, hopefully he already did, based the YouTube link that he, recording that he did. I'll also say that if you're interested in an implementation, and for example, you look at the All Gather plus Gem and you're interested in a video explaining that, open an issue and say, okay, could you please record the video explaining that piece of code, and we will do it. So I think at least for the one that I will do next is that I will do a deep dive into the library implementation. So maybe a 30 minutes video that will go through all of the all the low-level details of how the library works. We really want you to understand everything, and we really want you to contribute. So please, if you have ideas on applications, open issues, if you want to learn more through videos, please open an issue and just ask us, and we would be happy to record that for you. And that is the end of our talk. And I do apologize for coming late.
This was great, Mohammed. Thank you. I think you've certainly found a fan in the PM and chat and Vipul. So thank you. I think this is great. Like I kind of like these sort of small hackable distributed code bases because then like you can ramp up. You don't need a lot. You just like presumably need like a node to like do interesting experiments. We're doing a kernel competition. If you're interested in exploring some of these problems and you don't have access to like an MI300 node. I think there's like a couple of questions. Maybe we'll start going through them. I think I don't totally follow this is like, but Zoo asked a good question before, so I'm just gonna put him back on.
Yeah, I'm not sure if I follow the question. So float 4 sent from a wavefront to a mix 7 different GPUs have the same bandwidth as the same
Can I
GPU.
maybe I'll ask my own question, which is that like have you guys done any experiments with like very small D types? And does it fit basically what the work you guys have done already?
A quick note on I think one of the FP16 the implementation for the gem that we uses FP16 right now.
Yeah.
But we have a separate library that where we are testing all of these other precisions. FP4 right now isn't enabled, but F8 is using all of the PyTorch way of expressing sort of F8. But that's something on the list of things that we'd like to support, and we can add some unit tests that Iris is in fact working with these small types as well.
Yeah, but the beautiful thing about Iris is that, I mean, it's all written in Triton. If Triton can do it, then
Yeah.
do it. That's basically it.
I see. And then but Triton can do comms and low bit D types. Like sorry, it can do compute, but but supporting comms and low bit D types, like that
Well,
seems like an
it's
Iris specific thing.
basically, at the end of the day, it's basically like a load or store. So if T
Oh, I
always
see.
would generate the right instruction, then that should be enough.
There are
Got
most
it.
likely some level of optimizations that go along with it, like packing those small types all together before sending them through the network and things like that. That will likely be explored in the future, but from the functionality perspective, that should be a non-issue.
If you
Right.
are looking through the code and looking for something interesting that's novel about Iris that won't be found in other code bases, I think there was a discussion from the NVSHM talk, I think a couple of weeks ago with Jeff Hammond. He was discussing improvements from Shimon Pointer, which is allowing you to do direct load store access into other kernels or into other GPUs from a single kernel. That API with the Shimon Pointer is it's a legacy API from Shimon. The load store APIs with the cache modifiers within Iris are kind of a novel thing. It allows you to do cache placement from the load store, like Shimon Pointer, but it allows like even more control over it that you wouldn't even have with Shimon Pointer. Like for instance, I can cache it at like an L2 level or an L1 level. And do like very fine-grained placement in the caches. It's a very nice thing that it's a Triton
Oh, I
extension.
see.
Yeah.
And I see like maybe could you guys elaborate more because I think you very briefly many of you alluded to Gluon and like obviously like in Triton like I think that they don't give you access to like explicit like cache management but I presumably I think Gluon does but I haven't used it myself. Could you speak a bit more as to like why you think this is interesting like explicit like low level cache management is important for like the kinds of applications you're targeting?
If you look at the DeepSeek, the DPP code, they kind of hint at some performance improvement that you can get from doing like manual cache placement using like low-level assembly primitives inside that code. You can do similar stuff like that for other codes as well, where you try to minimize cache interference, cache pollution. If, for instance, you know you're producing data from a producer and the consumer is going to consume it in another GPU, you may not want to cache that data. It's kind of non-temporal. You're not going to expect any kind of reuse from your own cache. You're just producing and someone else is consuming. If you have other code that's running that's going to need cache lines, you may not want to pollute those cache lines with your data that you're just writing out. And these kind of cache modifier instructions allow you to do stuff like that. And you typically don't have access to these things unless you're writing the assembly by hand. So it like Triton exposes it to you through these cache modifier parameters, and it's a nice thing that being able to access a remote GPU's memory and specify what the cacheability of it is like a very nice thing.
And to add to that, I think one example on the compute side would be if your matrices, like if you have tall, skinny matrix problems, where one dimension is really, really large and you're doing matrix multiplication with it, and you have control over these cache modifiers, and you can fit an entire matrix. It's small enough. One part may be small enough to fit it entirely into your L2 cache, and the other one should never be cached, for example. It just never has some caching properties, like n dimension is really large, k dimension is really small. Then you can essentially apply these cache modifiers to make sure that the one there's no locality in it should never be cached and should avoid setting bits in the caches. There you can save some energy efficiencies. You can run your GPU clocks higher because of that. Your entire problem could run more effectively and more efficient and higher performance. It's that really like low level control that is just enabled through just one tag in the line, and that looks like what's shown in the slide at the top right corner. Cache modifier equals .wt right through. So it's really simple to add these very small modifiers to your load and store and experiment with in terms of getting potentially more performance out of your existing code. So the ability to be able to do that is really, really powerful.
All right. Well, I see another comment from PM, which is okay. I'll put it, which is like, oh, I think I see the problem across GPUs. Cross GPU scopes are not directly possible through a one-sided API. Yeah, I guess this is the main benefit of these like shared memory APIs.
Yeah, just one last comment on that. Like, one of the nice things about the Iris API is it has a load store API. You can directly access another GPU's memory, and like it loads it as a tensor from that remote GPU into your registers. The load store APIs do that. There's also a put get API as well that does essentially a memory copy from one memory space to the other. And so it's in line with what PM was saying about the cross GPU scopes. You're able to do that in Iris. It's very nice.
All right. Well, I don't see any more questions, but Mohammed, Brandon, thank you for coming. This was a lovely talk. Please come by again anytime you like. I guess we'll see everyone tomorrow. We're going to have another talk on mega kernels. And again, thanks again for our speakers for coming today.
Thanks for having us.
Thank you very much.
Thank you.
Thank you very much.